Okay, so we are in chapter 8. We are discussing reactions of alkenes. Actually, let me look at what sections in the textbook. So we will be discussing 8.4. Okay, this is what we are discussing right now, 8.4. Now, definitely read through sections 8.1 to 8.3. Okay, so read 8.1 to 8.3. They should not be that hard to understand based on everything that we've covered prior to this. Okay, but they don't deal with reactions themselves. There's some naming thing which we've already done. And then we are going to start with 8.4, which is the reactions of alkenes. So 8.4, this is hydrohalogenation. So this in some sense is the first reaction of alkenes that we're going to be doing. Okay, and we're actually also going to count how many reactions we are doing here. Okay, hydrohalogenation. Now, what happens in this reaction, to give you an overview, is this reaction converts an alkene into an alkyl halide. Okay, and I think it is useful to make notes like these as you study through these reactions, because we will be doing a few reactions, you know, I don't know, like approximately maybe 10 to 12 reactions maybe over the next 3 lectures. So it is very important that once we have a name and we know what the reaction is, we actually also know, okay, what does it do? Like, you know, why would I use it for if I have to use it for something? In fact, there's more detail that's missing here. So it converts an alkene into an alkyl halide, and usually, not usually, the more substituted alkyl halide is what's made. Okay, it gives us an alkyl halide, and it is the more substituted alkyl halide. Now, and again, as I've been mentioning, with all of this, it is always good to, like in your head, actually practice, connect it to everything that we've done before. So this reaction converts alkenes into alkyl halides. Do we know of a reaction that does the reverse of this? Alkyl halides become alkenes. What reaction is that? Think about that reaction. Okay, try to make a connection. So alkyl halide, starting with alkyl halide, getting an alkene as a product. That's an elimination reaction. Okay, E2 and E1. Now again, E1 competes with SN1, so we don't have to really worry about that, but E2, definitely think about E2. So bimolecular elimination would give you alkenes only as products. Okay, and that reaction, I don't know if I don't remember if I pointed this out, but that's called a dehydrohalogenation at that point. Okay, so that's the reverse of this. So always make these connections because they are useful, and also know what sort of product is formed. More substituted, less substituted. That's the terminology we'll be using in this chapter. More substituted, less substituted. Okay, on top of other things. So what happens in this reaction is when you have an alkene and you react this with HX, where X is a halogen. X is a halogen. Okay, when you react it with HX, you make an alkyl halide as your product. Okay, so alkene, start with an alkene and you make an alkyl halide as a product. And notice how this is the more substituted alkyl halide. The less substituted alkyl halide would be when the X ends up on that carbon. That would be the less substituted, and we're going to see that in a bit actually. Okay, so we get the more substituted alkyl halide. Okay, so as with anything, for all of these reactions, we are going to look at the mechanism to understand why does it happen like this. And we already know based on the overview that I did. So if you think about this reaction, what's going on here is we have an alkene. This is reacting with HX. So notice how HX, any X, okay, for any X, this is like an electrophile and a nucleophile because this H is del positive and that X is del negative. So it's like an electrophile and a nucleophile connected to it. And we already said that the alkenes, they behave as nucleophiles in these reactions. So what happens is the alkene goes and attacks the electrophilic portion of that molecule. X gets kicked out. So then we are going to make a carbocation, and we talked about this already. The more stable or the more substituted carbocation that's formed, okay, that's more favored, and that's the one that's formed. And plus, we are going to get X minus. And now the X minus is the nucleophile. You have a carbocation, so X minus comes and attacks that carbocation. And this would give us the nucleophile or the halogen in this particular case connected to the more substituted carbon. That is how we get our alkyl halide product. So that's the mechanism of this reaction essentially. Okay, that's the mechanism of this reaction. So we make the substituted alkyl halide. Now also notice that in this particular case, if R is something but methyl, then we are making a chiral molecule. But we'll look at some examples, okay, to basically discuss this. And we'll see some of those examples to discuss those. And now, so it proceeds through the more stable carbocation, okay, that's the intermediate. This is the more stable carbocation, okay. That's an intermediate. The halogen attacks that carbon and it gives us the product. Okay, so let's look at a few examples of this reaction. Maybe we will work out the mechanism for another specific example, and then we'll look at some other examples of what sort of products we would get. Okay, so if we start with let's say this alkene, okay, and we react this with HBr to be specific. In fact, actually, I'm going to change the example a little bit because I think this looks very much like the example that we just worked on. So let me add a methyl group over there. Let's say that's the alkene that we are using. We're reacting with this HBr. So when you get started on these problems, as you're trying to predict the product or something, look at your carbons. Notice how they are differently substituted. This carbon here has 2 substituents on it. That carbon has only 1 substituent on it. So we have a more substituted carbon and we have a less substituted carbon. Okay. So when the reaction happens here, the alkene goes and attacks the H, which is del positive, that's del negative. The Br gets kicked out. Okay, so let's see. Where's the carbocation going to form in this case? Think about that. We have a more substituted carbon, we have a less substituted carbon. So on this carbon, the first carbon here on the left, because that's the more substituted carbon, it would result in the more substituted carbocation. So carbocation forms here, H ends up over there. Okay, the hydrogen ends up over there. And plus, we are going to have Br minus. And now the Br minus goes and attacks the bromide, goes and attacks the carbocation. And this is going to give us I'm not drawing in the H because this is a bond line structure. So I'm basically, that's going in, okay? And we get this product here. So that will be the mechanism for this specific example. And now once we've made the product, okay, always look at it and predict if the carbon where the bromine is now attached, is that chiral, or is that a chiral center or not? Sorry, I think in my previous videos I said chiral, but the carbon's not chiral, it's a chiral center. So is this a chiral center? And in this particular case, it is not a chiral center because it has two ethyl groups on it. So we don't have to show any more detail, because in this particular case, again, the bromide can attack from both faces of that carbocation, but the product that we're making is going to be identical. It's not they are not enantiomers of each other. So we can just leave it over there. So that would be the mechanism for this. Okay, so it's an addition reaction where the HBr adds to that alkene, bromine ends up at the more substituted carbon, hydrogen ends up at the less substituted carbon, because the hydrogen is the electrophile, the bromine is our nucleophile. Okay, so with that, now let's look at this in a few different situations here. Okay, let's say we have a ring, an alkene that's part of a ring. So we have that alkene, and we react this with HCl. And I'm not going to work through a mechanism here, but I would encourage you to do that. I will draw the product. What product would we get here? Okay, that is what we're trying to see here. And what we know is the H, which is the electrophile, should go to the less substituted carbon. The Cl should go to the more substituted carbon. And in this particular case, this carbon here, which is part of the double bond, is the less substituted carbon. It has only one substituent coming out of it. But this carbon, the top carbon, is disubstituted. Okay, it has two substituents, so that's the more substituted carbon. So that means the product that I'll get in this case is going to be that, where the Cl is connected to the more substituted carbon, the hydrogen went to the less substituted carbon. We don't have to draw it out. And now, in this particular case, is there a chiral center? No, this molecule has symmetry in it. So this does not have a chiral center. We can just leave it over there. Okay. Let's look at another example. Let's say we have an example. I'm just trying to make it a little more complicated. Okay, let's say this is what we have. We have this example, and we react this with HI now. So kind of notice how I'm using like different HXs just to like impress upon you that doesn't matter, it's just basically an HX. Okay, so we do this reaction again for this alkene. You have a less substituted carbon on the left, the more substituted carbon is on the right. So that means the product that I'm going to get, symmetry issue. So let's just say that there is a methyl group here so that it's not symmetric now. Or we'll put it closer. Okay, let's say there's a methyl group over there. Okay, there's another methyl group there. So we have the alkene, that's what we are focusing on. So the product that we are going to get now and outside the ring, I have 1, 2, 3 carbons. So 1, 2, 3 carbons. Less substituted carbon, that's where the hydrogen goes. More substituted carbon, that's where the iodine goes. So the iodine ends up over there. And now in this particular case, we have a chiral center here. Okay, so that means we're going to make a racemic mixture here. Okay, so this is going to be a racemic mixture because we have a chiral center. And remember, you can show this by writing plus minus, dextrorotatory, levorotatory, or you could put the iodine on a wedge and write enantiomer, or you can just say racemic mixture. Any of those notations is fine, as long as you're basically saying that I understand that there's going to be a racemic mixture that's going to be formed in this reaction, okay? As long as we do that, I think we're fine. Okay, now, so those were a few examples. Now I want to show you another example because we also have to connect it to some other concepts that we've learned before, okay? And I'm going to give you a reaction here. So let's say we have an alkene like this. That's an alkene. You react this with HBr. Okay, so less substituted carbon, more substituted carbon. I would expect to get this product here. Okay, and again, notice this is a chiral center. Okay, so that means you will always get a racemic mixture there. I would expect that product to form. But it turns out in this particular case, we will get another product where the bromine is on that carbon, okay, on this carbon here, and not where I expect it to be. And this could sometimes be your major product, actually, depending on the situation, okay? That could be your major product. But we'll get both of these products. So the question is, how do we explain the formation of that product? What does it look like? Have we seen something like that before? Where something does not show up on the carbon we expect it to be, but on an adjacent carbon atom? Hopefully you're thinking about rearrangements, because remember there's a carbocation here. The carbocation doesn't care what reaction it is. If there is a carbocation and if there is a possibility of a more stable carbocation adjacent to it, then it will rearrange, okay? So what is happening here is mechanistically, why do we get both of these products? Because our alkene here, this reacts with HBr, so the alkene attacks the H, or the double bond, the pi bond attacks the H, Br gets kicked out, we get a carbocation like that, and I'm not showing the, you don't have to show the hydrogen, okay? You don't have to show the hydrogen because this is a bond line structure. The H attacks, it goes to the less substituted carbon. So you could just leave it like this. You don't have to show it because the hydrogen becomes part of that bond line structure. Get this carbocation, and plus you have bromide, okay? So now this is a secondary carbocation, and right next to it, there is a tertiary hydrogen, okay? So one possibility is the bromide comes and attacks this carbocation. And that's how we get to this product where the bromine is connected to that secondary carbon. So what we get is a secondary alkyl halide. But what could also happen is that we get a hydride shift. So the hydrogen shifts over. And this would give us a new carbocation, which is more stable now. This carbocation is tertiary. And then the bromide could attack that carbocation, and it would give us the other product. So carbocation rearrangement, okay, that's what's going on here. This is a carbocation rearrangement that explains why we get these two products. And this product, the unexpected product, is the major product, or that could be the major product because it comes through a pathway that involves a more substituted carbocation. Okay, so that is possible. So keep that in mind, okay, because we could encounter situations like that where we get rearrangements going on in the reactions. Okay, so that's the hydrohalogenation reaction of alkenes. Let's expand this to alkynes and see what happens when you get alkynes. So, okay, and I'm going to point out what section this is. So, hydrohalogenation of alkynes. Okay, when we go to alkynes, this is section 9.6. That's where it is, okay? So it is still a hydrohalogenation. Now, when you do the hydrohalogenation of alkynes, what happens is, in this reaction, an alkyne is converted into an alkyl dihydride. And again, this is going to be the more substituted alkyl dihalide. Okay, it's the more substituted alkyl dihalide that is formed. Okay, so essentially what we're saying is, to show you pictorially what's going on here, use a scheme. Okay, we have an alkyne, and now notice that I'm drawing it straight around this carbon. Okay, I'm drawing it linear about that carbon. Why am I doing it? Because this carbon is sp hybridized, and the geometry around an sp hybridized carbon is linear. Okay, there should be linear geometry around it. So you have an alkyne, and when you react this with, and in this reaction, the way we are going to consider this is when we react it with 2 molecules of HX. Sometimes you might just see excess written on it. That means there's more than one equivalent of HX. That's how you would read it. If it is specific, you're reading 2HX, but if it is says excess, read that as 2HX again, okay? More than one. So when you do this reaction, what you get is X and X. So an alkyne becomes an alkyl, because it's all saturated now, okay? It's an alkyl dihydride. That means there are 2 halogens now. X is still a halogen, okay, for us. So we get an alkyl dihalide in this reaction. How does this reaction work? Very similar mechanism here. So alkyne reacts with first molecule of HX. Pi bond, again, nucleophile, goes and attacks H. X gets kicked out. And what we will get is, now again, think about where the carbocation would form. There's possibility here, or there's a possibility here. This carbon is more substituted. More substituted carbocations are more stable, so the carbocation is found at the more substituted carbon. So what we will get is that, and we will get X with a carbocation over there. So I've attached the X to the less sorry, what am I doing? Not the X, but the H over there, and then we get the carbocation, and plus we have X minus. Okay, and then the X minus can go and attack that carbocation, and this would give us a vinyl. Okay, this is a vinyl halide. okay? So vinyl is basically when groups are connected to carbons that are double bonded, or sp2 hybridized carbons, or a double bond, actually alkene. That's a vinyl, because when it's a benzene ring, then they have a different name. They're called aryl halides, okay? So vinyl is when it's connected to a carbon that's part of a double bond. The halogen is connected to a carbon which is part of a double bond. So that's why it's called a vinyl halide, okay? But we are not at the final product here. Okay, now it is possible to stop it here, although it's like really hard, because now you've got an alkene, and we know that alkenes react with HX, so the reaction would keep going. Okay, so that vinyl halide now another molecule, or the second molecule of HX. So the pi bond comes and attacks the H, X gets kicked out, and this would give us X and a carbocation here. So I'm not showing, well, maybe let me show it in the mechanism. So this new hydrogen now ends up there. So kind of keep track of the hydrogens. There was one hydrogen here on that carbon to start out with. When we made this carbocation, there were two hydrogens. In this structure, I'm not showing those hydrogens, okay? But over here, you know, I think it is kind of confusing, but you know, that CH2 is there. Now the CH2 has an additional hydrogen, so it became a CH3 essentially. It is best not to show it, you know, because we should be able to count the hydrogens there, okay? So it becomes a CH3, we get a new carbocation plus X minus, and this carbocation is attacked by that X minus to give us the alkyl dihalide. That's how we get the alkyl dihalide. Okay. Also, I want you to take note of how hybridization changes have been reflected in this mechanism. This carbon was sp hybridized, like I said, so it was linear. But once we get to this carbon, this is sp, what would you say that is? Hybridization. I want you to think about that, okay? But think about the hybridization of that carbon, okay? I think that's very interesting. But I'm showing you some geometry over there. And then finally, we end with an sp3 hybridized carbon. So I'm showing that also over here, okay? So that's the mechanism of how an alkyne gets converted to an alkyl dihalide, okay? And we can do some examples here to show what sort of products will be formed. And again, as long as you identify that trend in terms of what's going on, in terms of like connectivity changes, I think it is very easy, okay? But you have to understand the connectivity changes here. So let's look at a few examples. So example, let's say I have this molecule and I react it with HCl, and we're going to say excess. Now, I think in some cases I've seen excess written as X and S. Read that as excess also, not extra small. It's like excess, okay? I've seen some people use that notation also, maybe including me, okay? That might have happened, but excess, okay? That's what we have here. So we have an alkyne, we have HX, excess of the HX. So alkyne should become the alkyl dihalide, and the halogens should go to the more substituted carbon atom, okay? I think it's always a good idea to count your carbons, okay? So I have 1, 2, 3, 4, 5. So essentially what we're saying here is we should get an alkyl dihalide at this, the dihalide, the two halogens should be at the fourth carbon, okay? So we get 1, 2, 3, 4, 5. So that fourth carbon has 2 chlorine atoms. That will be my product. And you can work through the mechanism again if you want, you know, just for practice, but that will be the product. let's try another example here. So we have that, and we react it with HBr and excess of that. So this carbon here, which is connected to the ring, that's where the two Brs up. So what we get here, our product, is going to be the dihalide. Okay, that will be our product here. Okay, so that's hydrohalogenation for alkenes and alkynes. Now what we're going to do is we're going to look at a variation of this. Okay, this sort of an addition, actually let me erase this and I will show you what I mean. So hydrohalogenation. So what we've seen is if we take an alkene and if you react it with HX, let's say, and I will show this for alkenes and it applies to alkynes also. Okay, so if you react it with HX, our product is an alkyl halide and it is the more substituted halide. But it turns out if I take the alkene, okay, this is a different pathway that we're going. So that's one pathway. This is the bottom different pathway. Okay, if you react it with HX, but now in presence of a peroxide. So to keep it very simple, let's think of H2O2, which is hydrogen peroxide. Okay, so HOOH, that's what it is. It does not have to be HOOH. It can be generalized for any peroxide. Okay, ROOR. So R is some alkyl group essentially. But when you do this reaction in presence of peroxide and heat or light, some sort of energy, okay, when you do this reaction, you get that alkyl halide now. So compared to this alkyl halide, now notice these alkyl halides are both coming from the same alkene. What's different is where is the X getting connected. In the top example, X connected to the more substituted carbon. In the bottom example, the X got connected to the less substituted carbon. Okay, that's the difference here. So this is the less substituted alkyl halide. Okay, so we can start from an alkene. We already know how to make the more substituted alkyl halide. This kind of an addition, like I mentioned, is called a Markov-Nikov addition. Okay, or a Markov-Nikov hydrohalogenation, to be very specific. The case where the X goes to the less substituted carbon on this alkene, this is called an anti-Markov-Nikov addition because the X ends up at the less substituted carbon. And because this is observed with peroxides, okay, so this is some peroxide, okay, because of that, this was also called, like people call it the peroxide effect, okay, that this is the peroxide effect. Because of the peroxide, it results in a different regiochemistry in some sense. Okay, this is an example of a regiochemical issue because the X goes to the more substituted or the less substituted. So we're going to look at this now. Okay, look at the mechanism of how the peroxide effect, or how do we get an anti-Markov-Nikov product. Okay, so hydrohalogenation, but we're talking about peroxide effect. And this is actually in, again, I want to make sure, I want to give you a reference as we go through these reactions. This is 10.10, okay? And for thermodynamic reasons, this hydrohalogenation, which is a peroxide effect, this only works with HBr. I'm not going into the details of why it works or why it doesn't work, but if you have time, please read through the textbook. It basically has to do with thermodynamics. You know, some of the steps are unfavorable when you try to do it with an HCl, let's say, or HI, you know. That's the whole point. So HBr, everything is balanced, so that works great. So it only works with HBr. It's a very important point, okay? So please take note of this. And what happens in this reaction is alkene becomes an alkyl halide, but now the less substituted one. Okay, it becomes the less substituted alkyl halide. Okay, so the general reaction I wrote here, alkene reacts with HBr and let's say ROOR, so some peroxide, and what we get is the less substituted alkyl halide as a product. Now, the fact that we are not getting the more substituted alkyl halide here tells us that there has to be a different mechanism that's operating here, okay? Because if it follows the mechanism of hydrohalogenation, then we will get a carbocation. Okay, regular, like a Markovnikov hydrohalogenation, then we should get a carbocation. And that carbocation must form at the more, would be favored at the more substituted carbon, and that would lead us to the Markovnikov product. But the fact that we're getting a different product, like the less substituted alkyl halide, means that it's probably not following that mechanism, okay? And which is true. So the mechanism of this reaction is actually a radical process, okay? It goes through radical intermediates instead of a carbocation intermediate. So what happens is there's an initiation step where your ROOR with heat or light, you need some energy to break it, okay? Let me check if the textbook uses any, yeah, it says heat, okay? But it's basically energy to break it, okay? What it does is it breaks homolytically to give you RO dot plus RO dot. So you got your initiator, your radical intermediate is formed, okay? What initiates the reaction. And then you have propagation steps, okay? And going back to free radical halogenation of alkanes, remember, this is where our products are formed, okay? So we have that. So essentially, what happens is this RO dot now reacts with HBr, okay? This reacts with HBr, free radical reaction here, brings an electron, HBr cleaves, splits, and it gives us ROH plus Br dot. So it is a propagation step because we've made a new radical. We started with a radical, we've created another radical. So that's an example of a propagation step. So we make a new radical, a bromine radical. And now the bromine radical reacts with our alkene, okay? It reacts with the alkene. So the bromine brings an electron. And now when the alkene breaks, again, you can put the bromine on the less substituted carbon or the more substituted carbon. But the bromine ends up on the less substituted carbon because that would give us the more substituted radical here, which is again more stable, okay? I'm not showing you both scenarios, but please work through it. So what we will get here is Br dot plus, sorry, there's no plus. We get that. So again, we started with a radical on the reactant side. We've got another radical on the product side, okay? And yeah, actually, in fact, this step here is also part of an initiation. Sorry about that, okay? That part is also part of the initiation. The actual propagation steps are only these two, because that's where the keep forming, okay? So we get the radical here, and now this radical reacts with another molecule of HBr. This brings an electron, that fragments, brings an electron, goes with the H. So this gives us product plus more bromine radical. Okay, so that's our product, the less substituted alkyl halide, and this bromine radical can now go back and initiate that step again. Okay, so initiation is all steps here, my bad. Okay. It is also two steps because the bromine radical is also sort of generated in the initiation step, because we don't have to go back to this step again. Okay, once the bromine radical is formed, it keeps regenerating and then it leads us to the product. So that's the mechanism of the free radical hydrohalogenation, the peroxide effect, and it gives us the less substituted alkyl halide. And the reason again is simple, because it leads or it proceeds to the formation of the more stable radical now, not a carbocation. We change the intermediate and the product changes. Okay, that is what we are seeing here. Okay, so that's the mechanism of the anti-Markovnikov hydrohalogenation. Only works with HBr, so keep that in mind. Let's look at a few examples here. Again with this one, so if we had an alkene like that, and if we did HBr and ROOR, heat or light, if we did this, what we're going to get is more substituted carbon, less substituted carbon. The Br should go to the less substituted carbon. So we are going to have that as our product. Okay, that's one example. Let's do another example here. More substituted carbon, less substituted carbon, HBr, ROOR with peroxide. Br goes to the less substituted carbon. So our product in this case is going to be this. Okay, and notice how in this particular case, this carbon is chiral. So that means we'll make a racemic mixture again, because that radical is also sp2 hybridized. So the attack can happen for both sides. Okay, so we get the more substituted alkyl halide as our product. Okay, and again, stereochemistry is there. So we're going to get a mixture of both products. This plus it's an enantiomer. Okay, so if I'm writing an enantiomer, then I have to show one of them as a wedge, or we tried plus minus to see that that's the product that's formed. Okay, and just to contrast, okay, maybe look at what would happen if we did this reaction directly with HBr. If I reacted that alkene directly with HBr, the product would have been this, the more substituted alkyl halide. If I reacted this alkene directly with HBr, the product would have been this alkyl halide. So we get the more substituted alkyl halide when you do a direct reaction with HBr, so the Markovnikov product, and you get the less substituted alkyl halide when you do the reaction presence of peroxide, which is the anti-Markovnikov product, okay? That's alkenes. If we extend this to alkynes, okay? So hydrohalogenation, if you start with alkynes, you will get alkyl dihalides, okay? And again, the less substituted alkyl dihalide. So if you react this alkyne with HBr, ROOR, and if we heat this, more substituted carbon, the triple bonded carbons, more substituted, less substituted, halogens should go to the less substituted carbon. So R, one carbon, and we get Br and Br. So we get alkyl dihalide. I'm not going to do any examples of this. I think it's very simple. Attach, again, realize in this particular case, this is with excess. If we don't have an excess, then we will get just one, okay? But I think for our purposes, we're going to use the alkyl dihalides, okay? So that is the hydrohalogenation reaction applied to alkenes and alkynes. Please practice a lot, okay? And we will look at more reactions of alkenes and alkynes. Bye.